Okay, guys. Now that we've it's cold in here, finished statistics, we're going to move on to the last 2 units of the year, which we have quite a bit of time now. I'm not really sure what's going to happen with our culminating and if we have to do any sort of exam prep. No one knows really what's going on, so we're just going to take our time, get through chapter 4 and 5, and then we'll worry in June what's going to happen in June. Okay, chapter 4 and 5 are both going to focus on statistical distributions. So we're going to start with a couple of the main types of probability distributions in chapter 4. It's a very short chapter. We're looking at taking maybe 4 to 5 lessons total for chapter 4. Just 2 of them this week. So the first one is basically an introduction to what probability distributions look like. And then from there, we'll get into a specific distribution called the normal distribution, which will be the focus of the entire unit. Is just going to be on one distribution. And then chapter 5, we're going to look at 4 or 5 different distributions. Okay, so a probability distribution is basically a graphical display of your data that takes into consideration how probable it is that it's going to occur. So you're really graphing some value, oops, I erased the x, of a random variable x versus the probability that that actually occurs. So in a probability distribution, it's always a variable on the horizontal axis that you're measuring, something like, in this case, the sum of 2 dice being rolled is the first example that's on your sheet, versus the probability. And the probability will range in scale depending on the scenario. So there's a couple different sort of terminology things that you're going to need to look at. The first is called a frequency table. So if it wants a frequency table, it's basically asking you to look at the comparison of your random variable that you've selected. In this case, we're calling x the sum when you roll 2 dice, versus the probability. So if I do a double sum chart like this, which we're familiar with, so there's a red dice and a green dice, and if you roll them, these are the possible sums you get. So you can get anywhere from a sum of 2, that means when you roll a 1 and a 1, up to a sum of 12 when you roll 2 6s. Okay, so these are all that occur. And obviously certain combinations of dice are going to come up more often. So the idea that a sum of 7 actually occurs 6 out of the 36 times means that it's the most likely sum that you're going to get. So when you roll 2 dice, the most likely one that you're going to get is a 7, followed by a 6 or an 8, which occur 5 out of 36 times, followed by a 5 and a 9, so on and so forth. The least likely outcome you're going to get is rolling 2 1s or 2 6s, which give you a sum of 2 or a sum of 12, because that's not that 2 1s or 2 6s are the least likely, but those are the only ones that make up that specific sum. Whereas 7s you can get by getting a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, so on and so forth. So basically what I've established here is our random variable that we're selecting in the first one, you always called x, is going to be the sum when you roll 2 dice. The second column of your frequency table tells you the probability that that occurs. Now, something of note, if you add up all of these probabilities, you will get 36 out of 36. Okay? What that means is there's a 100% chance of something happening in all probability distributions. The probability has to add to 1. You can't look at a scenario and say, oh, never mind, nothing happened. No, if you roll 2 dice, there has to be a sum. It didn't land on the corner and it's not quite on 1. No, 2 dice, they always roll, they land on something. So your probability column always has to add to 1. If you are forced to calculate some probabilities and you're not sure if they're correct, add them up. If they add to 1, chances are you've done them correctly. If they don't add to 1, chances are you've made a mistake. Okay, so that's called a frequency table. From there, we can graph it in what's called a probability distribution. That's what our concern is, this thing right here, a probability distribution. So I put all my x values, my random variables from 2 to 12 on the x-axis. And then on what traditionally would be a y-axis, or the vertical axis, we're going to put the probabilities. So we already see the probability of getting a 2 is 1 out of these 36 scenarios. And that's my first tick mark here. Now you'll notice I went from 136 to 236 all the way up to 636. I don't have to go higher because that's my highest probability that exists. When you're picking a probability scale, just look for your lowest and highest and pick something where the increments go up equally. So these are all going up by 136 by 136. You keep adding 136. So then in order to make the probability distribution, you simply draw a dot where this would match. The 0.2 and 1 over 36. The 0.3 and 2 over 36. And then you just kind of draw a line down. The main thing that we're going to be focusing on the next couple lessons, and not in this one yet, is what shape is this making? Okay, so this, if I kind of followed with a line, I had to graph this. This is the general shape of this specific probability distribution. Okay, and this shape is what we're going to do in 4.2, is actually what we refer to as a normal distribution shape. You may have heard of a bell curve, and that's basically what this looks like. It looks like a bell, okay, or an upside down bell. So imagine, ding, ding, ding. See what I mean? That's where the term bell curve comes from. And this is the most famous and the most popular distribution to do statistical analysis of. When you go to university and to college, they often analyze your marks on a normal distribution, and they want the majority of the marks to be in the middle here. Okay, so they want the frequency of marks somewhere in the middle to be the highest. They don't want too many people with really high marks. They don't want too many people failing out and they're not getting any money. They want the majority of you to come towards the middle. So sometimes there's some adjustments you can make to a set of data to make it fit a normal distribution. That's sort of a model that a lot of academic institutions will use. Okay, so frequency table, just a table of values, x, p of x. Probability distribution, just a graph of the frequency table. X on the horizontal axis, probability on the vertical axis. Okay, and then the last thing is called the expected value. So expected value is what are you expecting to get when you take part in whatever this probability experiment is. Okay, so in this case, what are we expected to get when we roll 2 dice? So the way we would analyze this is we would, here's this sigma again, standing for the sum. It's the sum of all the x's multiplied by their probability. So in this case, our first sum is 2, that's our x1. So imagine we called this x1. This x2, x3, x4 as you go down. And then this would be the probability of x1. So we're going to take x1, we replace the I with a 1, and multiply it by the probability of x1. So we have 2 multiplied by 1 over 36. We then want to add that to the next one, 3 multiplied by 2 over 36. Add it to the next one, add it to the next one, add it to the next one. And then you'll get a final answer. So that's called expected value. This is what we are expecting to get in whatever our probability experiment is. In this case, rolling 2 dice. So these are the 3 main terminologies I want to make sure that you had a verbal explanation of instead of just seeing what it looks like in reading. You'll notice on here there's a typo up at the top. It says it's lesson 6.1 probability models. Just in the past I had done this in a different unit, but it's been moved to as 4.1. Okay, so you should see this note generally looking like what's up here. Okay, these are the 3 main things that you have to understand, concepts from 4.1. I'm going to apply them to a couple of the examples. There are 5 or 6 examples in here. A lot of them are repetitive, so I'm trusting you can read them yourself. But I want to highlight the doing of another probability distribution and one that's a decent expected value type of question. Okay, so the first one I'm going to do with you is actually example 2, and then from there I'm going to move on to a different one. Okay. This week we're only doing 2 lessons just to kind of ease our way. Once we got through the midterm hump, we're not in a rush anymore. So again, I understand that you have multiple classes, and let me tell you, the motivation to get some of this stuff done, I get it, is a little bit difficult. It's getting more difficult for me to be motivated too. Okay, so example 2 says this. Determine the probability distribution. So as soon as you see this, the probability I always write distribution with a D-I-S-T apostrophe N. Determine the probability distribution for the number of heads. This is the key. This is going to be our X variable. If a coin is tossed twice. Okay, so what we really want here is a probability distribution. However, it's almost always imperative that we make a frequency table before we can make a probability distribution. So the idea of a frequency table is always going to pin two things against each other, x and p of x. The question is, what is your x? You have to decide what your random variable is. So in this scenario here, we're really looking at determine the probability distribution for the number of heads if you toss a coin twice. So this idea here, the number of heads, okay, really I should circle both. Let x represent the number of heads. That is really the random variable that we are dealing with in this scenario. Okay, obviously your other option is tails, but we don't care about tails. Our situation is asking us for the number of heads. Okay, so in reality, what you have here is when you toss a coin twice, what are the possibilities for number of heads you could have? Okay, so we could obviously have two heads. We could have a single head, or we could have no heads tossed. Okay, now if you look at a tree diagram, so maybe you're like, well, I don't know what the options are. So we go back to the first unit where we started looking at how do we count objects. So when you toss the first coin, you get heads or you get tails. When you toss the second coin, independent of what happened the first time, remember, we don't, just because you got heads the first time doesn't mean you're going to get tails the second time. It has no impact. They're considered independent events. You get heads or tails. Okay, so if you looked at the total outcome for each of these, okay, let me do it in a different color so we can tell. Follow this path, you get heads and heads. Follow this path, you get heads and tails. Follow this path, you get tails then heads. Follow this path, you get tails and tails. So now you're trying to match this outcome to what exactly the probability is. So how many outcomes do we have here? How many possible outcomes? Well, we have a possibility of 4 different scenarios. In how many of the 4, so these all have to be out of 4, do you get 2 heads, do you get 1 head, or do you get no heads? Okay, so obviously in how many of these out of 4 do you get exactly 2 heads? 1 of them. In how many do you get exactly 1 head? Well, you can have heads and tails or tails and heads. Both of those have 1 head. So we would say 2 out of 4. And then in how many do you get no heads? The combination that's tails and tails. So 1 out of 4. Reminder, what does this always have to add up to be a proper probability distribution? 1. So a quarter plus 2 quarters plus 1 quarter is 4 quarters, which is 1. Okay, so this is the frequency table. That's the beginning of how you set up the probability distribution. Once you have this, it's just a matter of graphing the two things against each other. On the horizontal axis, always your random variable. On the vertical axis, always your probability. Now, choosing the scale is different. You don't start with a 0 necessarily here. It all depends on your scenario. In our scenario, options are 0, 1, and 2. So we simply make those as our tick marks. You could have no heads, 1 head, 2 head. It's not a traditional scale where you start in the corner at 0 and grow up. You might have negatives even on this side, depending on what the scenario is. What are our probabilities? We could have 1 quarter. We could have 2 quarters. You can write 3 quarters here if you want, but we're not going to get up that high. And then you simply put a dot. What is the probability of getting 0 heads? 1 out of 4. Kind of just put a dot with a line down to make it look. You can put a little bar if you want. Doesn't really matter. What's the probability of getting a single head? 2 out of 4, which is the same as 1/2. What's the probability of getting 2? 1 out of 4. Okay, so that's in general what that looks like. Okay, now if on this, so we have a frequency table, a probability distribution. If I also asked you, find the expected value, so that's saying how many heads are we expecting to get if we flip it twice? We could do it like this. Expected value is the sum of the x's multiplied by the p of x's. Now we don't have to write the i's in, you get the idea. So you just take what is x1 in this case, well, we'll go in the order that we get here. Our first random variable, x is represented by a 0 with a 1/4 probability. So we take our x and we multiply by our p of x. We then add that to our next x multiplied by its probability. And then we add that to our last x, which is a 2 multiplied by its probability. Okay, and that's just a matter of solving. 0 times anything is 0. 1 times 2/4 is 2/4. 2 times 1/4 is 2/4. 2/4 plus 2/4 is 4/4, which is 1. So we are expecting, when we toss a coin twice, to get 1 head. And I think everyone would say, yeah, that's the expectation. We get 1 heads and 1 tails. Okay, that's generally the expectation. That's what we would call the expected value of this scenario. Frequency table, probability distribution, expected value. Okay, the 3 topics sort of this lesson. Okay, good. The other one I wanted to do, there's example 3 is talking about money with coin tosses, which is a great example. You can take a look at that on your own. Example 4 throws some combinations back your way. You can again look at it yourself. I want to specifically look at example 5 because that is a combination one that has some money involved in it, is an expected value, talks about fair games. So that's the one that has the most bang for our buck in terms of other questions. Again, you're sort of the value here that you have the notes in front of you while you watch this. You can pause it. You can take a look at what's going on. So if you're putting the effort in, I really think your chances of getting a decent mark in this class is probably better than if we were in school. So if you put the time in, there should be no reason you can't go. Okay, example 5 is a good one. This is where we start getting into kind of games of chance and games where we're sort of gambling and putting money on the line. So this is the game that was made up. A game consists of rolling a dice. Okay, so we know there's 6 options. If you roll a 1 or a 2, you win $5. Okay? Okay, so roll, I'm just going to put here, roll 1 or 2 equals win $5. Great. If you roll a 4, 5, or a 6, you lose $1.25. Okay? Determine the probability distribution for the winnings. Well, there's something missing here. If you roll a 3, nothing happens. So basically imagine I have this game set up at a table and I say, come play my game. It doesn't cost you anything to play until you find out your outcome. So you basically roll the dice. If it lands on a 1 or a 2, I hand you $5. Great, easy money. If it lands on a 4, 5, or a 6, you have to pay me $1.25. If you roll a 3, nothing happens. Okay, so that's the scenario. That's the game. We want to know, is this a fair game? Okay, what's the probability? What is your expected value of winnings, basically? What are you expecting to win? Okay, so it wants you to come up with the probability distribution and determine the expected winnings. Okay, so our probability distribution, we're going to set it up as a frequency table here. We don't necessarily need to graph it. So we have x and p of x. So in this case, because it's asking us, determine the probability distribution for your winnings. So in this case, let x be your winnings. Okay, the key to finding out what your random variable is looking at what they're asking you to find in the question. If you look at what they're asking you to find in your question, it's no problem. So our options here are, we have an outcome. So if we kind of put, what's our outcome here? Okay, these are the options. 1, 2, 3, 4, 5, 6. This isn't your x value because we're concerned about the money, not what you rolled. But obviously what you rolled determines your money. So this allows us to kind of set that up. So if you roll a 1, x is your winnings, you win $5. If you roll a 2, you win $5. If you roll a 3, you break even, nothing happens. If you roll a 4, you know what, to be fair, you really shouldn't have units in the column. Put it up there. If you roll a 4, you actually lose $1.25. If you roll a 5, you actually lose $1.25. And if you roll a 6, same thing. So we put a negative here because this is obviously positive winnings. That's you making money. This is you losing money. Okay, now what's your probability of each of these? Okay, 1, 2, 3, 4, 5, and 6. What's your probability of rolling any of those numbers? 1 out of 6. Each of these carries the exact same probability. Okay, so if we were going to graph this, just out of curiosity of what this would look like, and this is where I said this is not a traditional graph where it starts at 0, right? Your options here are negative 1.25, 0, and 5. Those are your only options. They happen to all come with a probability of, oh no, this is different, sorry. My bad. Let me fix that. Okay, your options are 1, 6, 2, 6, 3, 6, really. Because the chances of you losing $1.25 happens 3 times. So a 6 plus a 6 plus a 6, you have a 3 in 6 chance of losing $1.25. You have a 1 in 6 chance of breaking even, and you have a 2 in 6 chance of getting $5. So just looking at this alone, you're thinking, oh, well, I have a better probability of losing. You do, but when you win substantially more. So sometimes in games like this, you have to look at it in the long run. If you play a bunch of times, if your expected value is anything of over $0, then you should maybe play the game. Even though your chances are you're going to lose a couple times, more often than not, but you're only losing $1.25, whereas you're winning $5. So you'll see what happens. Again, our probabilities had to add up to 1, which we're happy about. So we now have what we would consider a probability distribution right here. We have a frequency table that kind of looks at it. The question is, how much are you expected to win? So expected value is X multiplied by the probability sum of all those. So our first X value, and we talked about this before, is negative 1.25. And what is the probability that's associated with that? A 6 plus a 6 plus a 6, 3 over 6. Add that to our next one. 0 is our next X value with a probability of 1 over 6. And then 5 is our next X value with a probability of 2 over 6. Okay, if you actually go about doing all this, let's see what happens here. Negative 1.25 times. Okay, you get negative 0.625. Obviously this one becomes 0. And this 10 over 6 becomes 1.667, we'll say. So if we round it to the nearest kind of value here, our expected value is actually $1.04. Okay, I think on the note I have $1.03. I obviously rounded earlier to 63 here and $1.67 there. Whatever it happens to be. $1.04 is our expected value. So we're actually expected to win in this game. In the long run, maybe you play once, you lose $1.25. Maybe you play twice, you lose $1.25 again. So now you're down $2.50. But maybe on the third time you play, you win $5. Now you're up $2.50. The longer you play, in the end, your expected amount of winnings is $1.04. Okay, so that is considered a unfair game. Why is it considered unfair? Because the expected value is not equal to 0. It's more than fair to you is what it is. It's not fair to the person running the game. But the idea of what fairness is in this scenario is when the expected value equals 0. When you're expected to break even, that's considered fair. Okay? Every casino game is unfair. Every single one is its expected value is a negative number. No one is expected to win in the casino. Do people win? Of course they do. Do more people lose? Yes. Okay? The game at the casino that's the closest to you having a chance of winning is blackjack, and that's only if you play by the correct rules and only if everyone else at your table is playing by the correct rules. And then it's somewhere around 48% chance that you'll be on the winning side. Okay? You're still not going to be. It's not over 50%. So your expected value is still in the negatives no matter what game you play. Okay. So that should kind of take care of 4.1, there is homework listed here, page 374, 1 to 6, 8, 10, and 11. So you can get started on that. And then the next one for this week, the week of today's April 21st, to get us through until, I guess, the 28th, really, next Monday, by the time we go to 4.3, will be just this and 4.2. Okay.